Hello, this is Brian Washburn. I'd like to give an introduction to Hamilton's principle. So let's take a look at what I have here. So here I'm plotting the position, a solution to, say I have a particular mechanical system, and a particle, its position as a function of time is given by x of t. And so I'm plotting x of t from one time t1 to time t2. And if we were to solve using, say, Newton's equations, in order to, what we'd do is we would write down the net forces acting on the particle. We'd solve a second order differential equation and we get x as a function of time. And then we plot x as a function of time, we would get that solution. And so that is a way to solve a mechanical system. But people started asking a little more kind of different questions about this, and they asked, well, given particular forces or constraint on the system, why does it take this particular solution? Okay, if I call this solution, say, a path, okay, meaning it's a position as a function of time, why is this particular path the solution to that mechanical system? All right, for example, why doesn't another path, if I have another path that, say, does this, the same two starting and ending points, why isn't that a path to the mechanical? Why is that also a solution? So why does the mechanical system choose this path and not that path or any other path? Now we can answer that using Newton's laws. You can say that, well, I can write down a mathematical expression for the red line, and I can show that that mathematical expression doesn't satisfy Newton's second law. Okay, but again, Newton's laws are kind of rules; they're axiomatic. And so the question is, okay, so it follows the rules, but is there something deeper going on? Is there some deeper understanding of motion that we need in order to describe what's happening? Okay, so people started trying to answer this particular question, and the method they tried to use was the method of the principle of least action. All right. Okay, so the idea of this principle of least action started to occur in the mid to 1700s. Again, Newton developed Newton's laws in the year 1666. So about almost 100 years after Newton developed his laws, people started asking this question. And the question was, for a given mechanical system, why does it follow a specific path, x of t? And people said, well, then maybe what happens is, for that given path, there's some physical quantity that is maximized or could be minimized. Okay, we use the term stationary. Stationary means that when I take that physical quantity, I look at it and it's at either a maximum or minimum. These ideas, the least principle ideas, Marpatui came up with this idea of least action in 1747, but really didn't have a strong mathematical idea of what was being minimized. It was more of a concept. What we're going to be learning in the next few weeks is a form of mechanics called Lagrangian mechanics, which is based on a principle of least action. And so Lagrange came up with his form of mechanics in the 1760s. But today what I'd like to talk about is the work of Hamilton, or more specifically what's called Hamilton's principle. And by the way, that's different than Hamiltonian mechanics, which we'll learn even later this semester. So I like to talk about what is Hamilton's principle. What Hamilton's principle does is it takes the idea of least action and talks about what is being minimized in a particular physical system. Okay. However, before I talk about Hamilton's principle, it's really important to realize that even though I'm describing a mechanical system using a principle of least action, it doesn't say that Newton's equations are wrong. If I develop another formalism of mechanics, not based on Newton's laws, but a principle of least action, I better get, in the end, Newton's equations. Okay, so I better get the same result I get from solving the equations with Newton's equations. So in some respects, even though it's interesting, if you think about it, we're using a different principle to solve mechanical systems, but we're not going to learn new physics from it, because in the end we get the same second order differential equation we'd get from Newton's equations. Now you might ask, well, why just use Newton's equations? Well, in the end what we're going to learn is these mechanical systems using these principles, specific Lagrangian and Hamilton mechanics, are a lot easier to solve using those forms of mechanics than Newton's laws. And we're going to do many, many examples throughout the class. So this principle of least action better result to Newton's laws. But what is being minimized, or what is this action? Okay, and that's what Hamilton's principle is. So let me just state Hamilton's principle. And Hamilton came up with this principle in the mid 1800s. Okay, and basically it says this, that the actual path, again, the path is x is a function of time or something like that, which a particle follows between 2 points 1 to 2 in a time interval t1 to t2 is such that the action integral, where the action integral s is the result of the action integral, is equal to an integral of a function L from t1 to t2, where L is called the Lagrangian, and the Lagrange is defined as the kinetic energy minus the potential energy, okay, such that this is stationary taken along the given path. What that means is if I choose the actual path, I do the integral, I get a minimum, I minimize the Lagrangian, I minimize that function. That's Hamilton's principle, okay? And you may question, well, why is this principle true? Okay, well, that's a good question. But the Hamilton's principle is the foundation between Lagrangian and Hamiltonian mechanics. And we're going to show that if we take that foundation, we're going to get the same results for a mechanical system that we would get using Newton's equations. Okay. Now, remember, what we're trying to do is the Lagrangian is a function of x and x dot. Okay, Lagrangian has kinetic and potential energy. The kinetic energy is a function of x dot. The potential energy is a function of x. And remember, what I'm trying to do is I'm trying to find a function x that minimizes this integral. So doesn't that mean I have to consider all possible paths, an infinite number of paths? I have to choose one of those to satisfy this integral. That seems like an impossible task. Okay. In fact, however, we can do that. Okay, so again, what we want to do is find x and x to t, which is our path that minimizes the integral. Now that problem has been solved, and that solution comes from a method of mathematics called the calculus of variations. And the calculus of variations is a variation principle. And basically the calculus of variations in some respects says I try to find a function x of t that minimizes this action integral. Okay, so let's talk a little bit about the calculus of variations. All right, and we're going to spend a lot more time, but I just want to give an introduction to it. Originally, the calculus of variation was posed as, okay, say I have some function, and that function is a function of, now here instead of having x to t, I have a trajectory. So here I'm expressing this as a spatial function. Okay, so basically I have some arbitrary function as a function of y, a trajectory, y is a function of x, and the velocity is a function of x and x. Or actually, this is not velocity. This is the rate of change of the prime is the derivative with respect to x. So that's dy dx. Okay, and so it's a slope actually. Okay, so the question is, I have a function, some arbitrary function that's dependent on y, the slope, and of x itself. What path will minimize or maximize this particular integral? Okay. Well, that path satisfies this particular differential equation, and this differential equation is called the Euler-Lagrange equation. Okay, so in the end, the way to solve this problem is I write down my function f. Again, I know f. What I don't know is y of x, and so what I do is, however, I take derivatives of x, but f is a function of y and y prime and x. I take the derivatives, put it into this equation, and solve. Now, in the end, this looks like a differential equation, but really it's, well, okay, I will get a differential equation out of this, and I can solve that differential equation. Okay. Now, so what problems do you solve with the calculus of variations? And there's a couple problems that have been kind of famous problems, and we're going to look at some of these problems in class. Again, this is not Lagrangian mechanics yet. This is just calculus of variations. One problem is, say I have 2 points in space. Find the curve that So other problems that use the calculus of variations, again, classical problems, is we mentioned Fermat's principle. Fermat's principle is an alternative way to get Snell's law. So if I have light that goes from one medium to another medium, the path it takes is the path that minimizes the time between the two media. And we'll look at this problem. And then the final problem, another classical problem, the brachiosynchrone problem is, say I have a particle that exhibits constant gravity. What's the path of the shortest time under that force? Okay. So again, these problems here deal with solving for y as a function of x, some trajectory in space. When we use the calculus of variations, what we're going to do is we're going to get a Euler-Lagrange equation, except the path that we're interested in is not y as a function of x, it's going to be x as a function of time. And so I'm not going to show the solution to this, but really when we're going to use, so what we're going to do is we're going to be using, so again, Hamilton's principle is the fact that this quantity called the Lagrangian, the action integral of that is minimized for any physical system. And so in order to find that path, or x of t, we have to use the calculus of variations to do that. Okay. Now, when we do this, okay, and by the way, let's generalize the problem even a little bit more. Remember, some problems you solve for x as a function of time, y as a function of time, sometimes theta as a function of time. So I'm going to define something called a generalized coordinate, q, q of t. This is my path, okay? And q, for example, q might be x, it might be an angle, it might be something, some coordinate. It's a degree of freedom, okay? Now, if I have a q, I have also a generalized velocity, which is q dot, okay? And q dot could be a speed or an angular speed. And in general, my kinetic energy is going to be a function of q dot, and the potential energy is going to be a function of q. And so again, according to Hamilton's principle, we want to minimize this function called the Lagrangian, which is the kinetic minus potential energy. And to find the path, or q of t, we're going to solve this differential equation right here. Now, in the end, what are we going to get out of this? Okay. Well, when we stick our function L, so our procedure in Lagrangian mechanics is calculate the kinetic energy, calculate the potential energy, calculate the Lagrangian, put it into this equation here, and solve. When we finally we're going to get a second order differential equation, which is exactly the same second order differential equation we would get using F equals ma. So there's no new physics involved. Okay, we get the same second order differential equation. We get the same equation of motion, and then we still have to solve that to solve. So then you may ask yourself, well, why do that? This seems very complicated. Why don't I just use F equals ma? Well, that's the thing. For very difficult problems, solving the Euler-Lagrange equation is going to be a lot easier than trying to set up F equals ma. Okay, and in the end, we'll get the same equations of motion, and then we still have to solve that second order differential equation. So the best way to learn how to use Lagrangian mechanics or use the Euler-Lagrange equation mechanics is to see a lot of problems, and that's what we're going to do in class. So we'll see you there. Bye-bye.